Okay, let us finish off chapter 3 by looking at the final section, which is rearrangements. Rearrangements. And this is actually a very fascinating subpart because it has some very bizarre results. Okay, let us first define what it means for by a rearrangement. Definition: let Kn be a sequence in which every positive integers appears be a sequence in which every positive integer occurs exactly once. Occurs exactly once. It is to say once and only once, which is to say it is a one-to-one function from the set of integers Jn. Well, whatever. Okay, many ways of defining it. Then put a prime of n is equal to a of kn. Okay, putting a prime of n is equal to a of kn, we say that summation a prime of n is a rearrangement of summation an. Okay, so basically you are reordering the terms of the sequence and you are going to get completely different things. Okay, it's a completely different sequence. In general, if Sn and Sn prime are the partial Sn prime are sequences of partial sums, mm, partial sums of summation an comma summation an prime, then as you can see, these sequences are generally completely different. These two sequences generally consist of um, entirely different numbers. Right? So that brings the question of whether the series S converges, whether the um, series S converge, and if they converge to the same thing. Question. Does a rearrangement converge? Rearrangement converge, and if it does, does it converge to the same limit? Does it converge to the same limit? Now, the intuitive idea might be, yeah, they're the same numbers, right? Even if I mix and match them. For finite sums, you know the property that, like, even if I reorder a summation, 1 plus 2 plus 3 plus 4 is same as 1 plus 4 plus 3 plus 2 is same as 4 plus 2 plus 1 plus 3, right? The, the arrangement does not matter. So question becomes, is that true even for infinite sums? And as it turns out, it is not the same. Okay, so example, consider this convergent series. Consider the convergent series 1 minus 1/2 plus 1/3 minus 1/4 plus 1/5 minus 1/6 plus dot dot dot. Okay. Why is this convergent? Convergent by alternating series test. Alternating series test that we saw before. Okay. The signs are alternating, the limits are going to 0, so it converges. Okay. Now look at its rearrangement. Look at one of its rearrangements. Arrangements 1 plus 1/3 minus 1/2 plus 1/5 plus 1/7 minus 1/4 plus 1/9 plus 1/11 minus 1/6 and so on. Okay, so the pattern is plus dot dot dot. 2 positives, 1 negative. 2 positives, 1 negative. Okay, so if S is the sum of the first term, so let us look at this one. Okay. Oops. This converges by alternating series test, and if you look at the partial sums, if you look at the first 3 terms, you get 1 minus 1/2 plus 1/3, which is 5/6, and then every term you have minus 1/4 plus 1/5, which is smaller than 0, minus 1/6 plus 1/7, which is smaller than 0. So if I call this as S, okay, convergent, let's say, suppose this converges to S, okay, then let me call this S1. Then S1 is smaller than 1 minus 1/2 plus 1/3, which is equal to 5/6. Right? However, if you look at the second series, if you look at this series, I'm not going to show that it converges. Okay. It does converge, but if you look at it, the pattern is 1 over 4k minus 3 plus 1 over 4k minus 1 minus 1 over 2k, and by calculation this is positive. Okay, hence therefore S prime of 3 is smaller than or equal to, actually strictly smaller than, S prime of 9, S prime of 6 is strictly smaller than S prime of 9, strictly smaller than dot dot dot, if you look at the sum of every 3 things. Right? So this is my S prime of 3, S prime of 6, S prime is equal to limit of this. This is S prime of 9. If I take 3 things at a time, they're positive. Okay? And therefore, S prime is greater than S prime of 3, which is equal to 5 over 6. Okay? Therefore, the series S prime, or the rearrangement, let me call this an prime. Therefore, an prime definitely does not converge to 5 over 6 as lim sup n goes to infinity s prime of n is greater than 5 over 6. Right? And so from this we see that therefore rearrangements need not converge to the same number. Do rearrangements have to converge? Well, before we answer that, let us look at a very interesting theorem, which is by Riemann. Theorem 3.54, Riemann. Okay. Let summation an be a series which converges but not absolutely. Be a real series which converges but not absolutely. Okay? Suppose we have that negative infinity is smaller than or equal to alpha, is smaller than or equal to beta, smaller than or equal to positive infinity. Okay? Then there exists a rearrangement summation a n prime with partial sums Sn prime such that lim inf of Sn prime is equal to alpha, lim sup of Sn prime is equal to beta. Okay? In particular, this means not every rearrangement converges. Not every rearrangement converges. And given any A, and given any alpha, there is a rearrangement which converges to alpha. Okay? So given any number A alpha, you can always find some rearrangement of the series that you can make it converge to alpha. Because you can take alpha is equal to beta, and then the sequence rearrangement is converging. Proof. This is a slightly tricky and a slightly smart proof. Quite interesting. So I want to do this. Pn is equal to absolute value of an plus an over 2, and Qn is equal to absolute value of an minus an over 2. Okay, for every n. Then Pn plus Qn is equal to absolute value of an, and Pn minus Qn is equal to an. Okay. Now, note that both these series must diverge. Note both Pn comma Qn must diverge. Why? If both of them converge, if both converge, then summation Pn plus Qn is equal to summation An converges. Okay. And if only one of them converges, if only one diverges, then summation Pn minus Qn is equal to summation An. This would diverges. Okay. So it is interesting that both of them have to converge. Both of them have to diverge at the same time. Okay. So we will let Pn denote the what do you call it? Let P1, P2, P3 denote the non-negative terms. Negative terms of summation An in order of which they occur. In the order they occur. Okay, so only the non-negative terms, not the positive terms, not the negative terms. Okay, and let Q1, Q2, Q3 denote the absolute values of the negative terms. Be the absolute values of the negative terms of it. Negative terms of summation An, also in order. Also in original order. Okay. So what is it? So the partial sums of An are going to be some P1, P2, Q1, Q2, something like that. Okay, we don't know what the exact thing is. However, what we know is, therefore, summation Pn, comma summation Qn differ from summation Pn, comma summation Qn only by zero terms. Only by zero terms, and hence both diverge and are therefore divergent. Right? Why is this true? If you look at Pn, if An is negative, absolute value of An plus An is 0. So if An is negative, Pn is 0. If An is positive, Qn is 0. So in every term, either Pn is 0 or Qn is 0. Okay? The summation capital Pn ignores all those terms of Pn which were 0. Summation capital Qn ignores the terms of summation Qn, which were 0. Okay. So now we shall construct sequences. Construct sequences mk, comma kn, mn, sorry, not mk, mn, comma kn, such that the series p1 plus p2 plus dot 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 up to pm1 minus q1 minus q2 all the way up to minus qk1 plus pm plus 1 m1 plus 1 up to pm2 minus qk1 plus 1 plus dot dot dot, sorry, minus, not plus, minus dot 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 minus qk2, right? Yeah, k2 plus pm2 plus 1 plus, and so on. Now this is clearly a rearrangement of summation an, which is clearly a rearrangement of summation an satisfies limit n goes to infinity infim s prime of n is equal to alpha lim n goes to infinity supremum s n prime is equal to beta. Question: why can we do this? Okay, how can we construct such things? If we want to do this, how can we construct such two things? Well, here's how we are going to do this. Choose real valued sequences alpha n and beta n. Choose real valued sequences alpha n, comma beta n, such that alpha n converges to alpha, beta n converges to beta. Okay, and because I have that alpha is smaller than beta, I can actually choose these sequences so that alpha n is smaller than beta n for every n. Okay. Now technically I'm saying that beta can also be negative, but for convenience I'm going to take beta 1 greater than 0. Okay, I'm allowed to have beta n to be even beta to be negative infinity, that's fine, but I'm going to take beta 1 greater than 0. Okay, let m1 comma k1 be the smallest integers, such that p1 plus dot 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 plus pm1 is greater than beta 1, and p1 plus dot 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 plus m1 minus q1 minus dot 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 minus qk1 smaller than alpha 1. Okay. Why can we do this? Because both summation PM and summation QM diverge. If there was no such M1, then summation PM is bounded above by beta 1, which means it doesn't diverge. If there is no such Q1, QK1, sorry, if there is no such K1, then summation, what do you call it? Q, summation Qi is bounded by alpha plus P1 to PM1, which means again that summation Qi has to be bounded. Since both of those are unbounded and divergent, we can find this. Okay. Then continue doing this. Choose let M2 comma K2 be smallest integers such that, well, now that I have this one term first, P1 plus dot 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 plus PM1 minus Q1 minus dot 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 minus QK1 plus PM1 plus 1 plus dot 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 PM2 greater than beta 2. This entire nonsense, P1 plus PM1 minus Q1 minus QK1 plus PM1 plus 1 plus dot 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 PM2 minus QK1 plus 1 dot 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 minus QK2 smaller than alpha 2, and continue this process. Okay. This is always possible because summation Pn and Qn diverge. Okay. Now, I have this. Okay. My terms summation PM1 are greater than beta 1, greater than beta 2, greater than beta 3. So how do I guarantee that it is actually converging or diverging to alpha and beta properly? So let me call these sequences, call this sequence as a star. Okay. Star. So in that case, let xn and yn denote the partial sums of blue star, which are whose last terms are Pn, Pmn and Qmn, Qkn, Qakn. Okay. Well, then xn minus beta n is smaller than or equal to Pmn, and yn minus alpha n is smaller than or equal to Qkn, right? Because I chose them to be the smallest one such that this condition is satisfied. If this was greater than Pmn, then I didn't need Pmn. I could have taken Pmn minus 1. If this was smaller than or equal to Qkn, I didn't need Qkn. I could have stopped at Qkn minus 1, and the property would have been satisfied. As Mn and Kn are the smallest integers satisfying their condition. Satisfying their condition. Okay. Well, great. However, limit Pn is equal to 0 and limit Qn goes to 0. Both of these are going to 0, and therefore xn goes to beta and yn goes to alpha as needed. Okay. And that finishes the proof. Okay. You can. It is easy to show that these are indeed the lim_sup and lim_inf. Okay. It's a very small argument, but it is clear that no other numbers can be lim_sup and lim_inf. So this is what you're going to get. Okay. That means that every rearrangement, not every rearrangement, every given alpha and beta, you can find a rearrangement such that they are the lim_sup and lim_inf, and in particular, given any number alpha, you can find a rearrangement that is going to converge to it. Okay, which is a really strong theorem. So if you want to find the sum of a sequence which is not of a series which is not absolutely convergent, you cannot rearrange the terms as you like. You will get a different sum. You have to be really careful, which makes life harder, right? Theorem 3.55. This tells you that life is good if your series does converge absolutely. If summation an is a series of complex numbers, is a series of complex numbers which converges absolutely, then any rearrangement of summation an, then every rearrangement of summation an converges, and they all converge to the same sum. Converges absolutely, and they all converge to the same sum. Okay, so if your series converges absolutely, life is great. All of them are going to converge to the same exact thing. You can rearrange them however you want. Life is awesome. Okay, how do I prove that? Well, let summation an prime be a rearrangement. Be a rearrangement with partial sums Sn prime. Okay. Now, if the series converges absolutely, then given epsilon greater than 0, there exists n such that for every n greater than, well, by convention of the book, m greater than or equal to n greater than or equal to capital N, we have summation I is equal to n to m absolute value of ai, not an, is smaller than or equal to epsilon. Right? The Cauchy criteria for convergence of absolute values, for absolute convergence, not convergence of absolute values. Well, right? All right. Now choose P. Now choose p such that the integers such that the integers 1 dot 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 n are all contained in the set are all contained in the set k1 dot 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 kp. Okay, following the notation of the definition which we started with. So this is my definition of rearrangement. I am defining kn. That is what I'm using. Oops. Scroll too much. Okay. Great. So this is a much bigger set, k1 to kp, than 1 to n, but it's going to be a finite set, right? At some point of time in a rearrangement, find the last element where you hit 1 to n. That's set that as your p. Then 1 to n fits in k1 to kp. Then, if n is greater than p, the numbers a1 to an will cancel the difference. Sn minus Sn prime. Sn prime. So that Sn minus Sn prime is smaller than or equal to epsilon, right? Because what is happening? What is the major provider of the difference? A1 to an will cancel in the difference. That's what I thought. I wrote that wrong. Cancel in the difference. What is going to happen? A1 to an are in both Sn as well as an S prime of n, not Sn prime. Why happen? S prime of n. They're in both of these sets, so they cancel, and everything else satisfies summation is smaller than or equal to epsilon, right? So this sum is smaller than or equal to epsilon. Since this is true for every epsilon, as this is true for every epsilon greater than 0, you have that Sn prime converges to S. Right? And hence, both of them converge to the same exact limit. This is a shorter video. I am going to stop here, but we have actually finished the chapter. I might make another video, a small video, maybe doing some of the problems. I will try to write out solutions for the exam soon. Okay, but that might take me a day or two more because I'm trying to finish grading for the other course I'm teaching first. I finished the grading for your course first. I'm still doing it for the other course. Since I was unwell, it was delayed. I will upload this, and yeah.